Okay, so I'm happy to invite Kenny to give a talk in our machine learning seminar. Kenny is currently a full professor of computer science at Shanghai Jiao Tong University. He got his bachelor degree and PhD from National University of Singapore, and he was also a postdoctoral researcher and lectures at Princeton University. And Kenny has a very wide range of collaboration with industries as well, such as Microsoft and Google. His current research is basically natural language processing and knowledge engineering. And he has published many papers in the best conferences in AI and NLP, such as ACL, AAAI, IJCAI, SIGMOD, etc. And his research has also been supported by many funding agencies like NSF China and MOE China, Microsoft, Google. He is also a winner of the 2013 Google Faculty Research Award and 2015 DASFAA Best Paper Award. So I will hand over to Kenny.
Okay, thank you very much, Kenny, Kai-Chi, for the introduction. So I'm very happy to be here and present you a bit of our recent work in dialogue and text generation. So Adapt Lab is the name of my group, and actually Kai-Chi was an alumni from this lab, and he was actually one of my best students. So I'm very happy to be back and to join this webinar. So all right, so today I'm going to talk about these few things. I will first give you a bit of overview about SJTU and our lab, and then I'll talk about 3 topics. And these were actually 3 recent papers. So the first one is going to be a dialogue response selection, which was published at EMNLP 2020. And the next one will be clarification question generation, which is going to be published at the Web Conference 2021. And finally, Abstractive Summarization, also a paper to be published at the WWW 2021. Okay, so before talking about our lab, let me introduce to you guys a little bit about our university and our department. Okay, so essentially SJTU, or the short for Shanghai Jiao Tong University, is one of the top universities in China. And its computer science department is also one of the strongest in China and in the world as well. And this slide just shows you the CS ranking for the last 5 years. All right, and you can see that Shanghai Jiao Tong University is currently ranked world number 31, which is just behind Tsinghua University and Peking University, 2 of the top universities in China. So we actually hold similar rankings at the other well-known university rankings, such as the QS ranking, US News, and the academic ranking of the world universities, which happens to be hosted by, previously hosted by Shanghai Jiao Tong University as well. Okay, so that was sort of just to give you a sort of an overview of how we stand in terms of computer science. Okay, then let me talk a little bit about my own lab. Okay, my lab is called Adapt Lab, and we primarily do research in natural language processing and knowledge engineering. So that includes natural language understanding and natural language generation recently. So I primarily publish at places such as AAAI, IJCAI, and ACL related conferences. So currently my team includes myself and 5 PhD students and 12 master's students, as well as a couple of undergraduate students as well. So, so today I'm going to focus on the natural language generation part. All right, the first thing I'm going to talk about is called the multi-turn dialogue response selection. So this is actually one of the important tasks in natural language processing today. So I will first give you a brief description of what this task is about. All right, so essentially a multi-turn response selection is a problem where you're given a dialogue context which essentially contains two or more persons' utterances. Like in this case, we have a session between two persons, A and B. So, and this particular conversation actually took place in the context of Linux administration. Okay, so these guys are actually talking about certain packages, whether it's going to be released or not. So somebody was anticipating for the release of a certain tool package. All right, so the problem here is that given that A and B have already made these utterances in turn, which we call multi-turn, and we are supposed to produce a response. And this response is supposed to come from B, and it's supposed to be chosen from one of the following candidates, one of the three candidates, the small letter A, B, and C candidates. Okay, so for our humans, right, it's actually not so difficult for us to pick number A to be the right response, okay, because that one was also talking about Linux, and it's actually talking about the release date of that particular package. So that's the right response. So in this task, we are supposed to develop an algorithm or a model that can, which takes as input the context and then produce an output which selects from one of the given candidates. Okay, and the candidate is supposed to be number A in this case. Okay, next, let me give you the motivation behind our approach. Okay, so I'm going to talk about firstly a number of previous approaches to tackle this problem. All right, in general, the previous approaches can be divided into the following three categories, and they are sequential models, hierarchical models, pre-trained language models. All right, let me talk about these three approaches in turn. So for sequential models, essentially, we are given during training, okay, during the training of this model, which is shown here, right? We are given the input, which is the context that I showed you before, also known as the dialogue history, right? And then we're also given the possible candidate outputs, okay, which are the responses. So in the case of the previous example, we were given three different candidates, right? So one of the candidates was a correct candidate, and the other two are incorrect, right? So the model actually takes these two, takes the input and the output at the same time. So what the sequential models does is that it concatenates all the utterances within the context into one long string, okay, or long sequence. But it does mark the end of each utterance with the EOU tag, which stands for end of utterance. All right. So and then basically you have a long sequence, and then the response is also a sequence of words. All right. So both of these sequences are fed into typically a sequence encoder, such as a bidirectional LSTM. All right. And the output of this will be a vector representation of both the input sequence and the output sequence, right? And then these two vectors are going to be fed into this multi-head self-attention pooling, right? This mechanism that basically tells you the relationship between certain elements, certain features in the input with certain features in the output, as well as within the input themselves and within the output itself. All right, and then we send this the combination of these two vectors into this multi-layer perceptron, which classifies into whether it's a true label or false label. All right, so it gives a matching score in the end. So this is the basic sequential approach. All right, so for the hierarchical models, the difference is that instead of concatenating all the utterances into one long sequence in the very beginning, we don't do that. We instead send each utterance in the context into this encoder, okay? And it encodes into certain multi-grain representation. So depending on the actual approach, there may be some differences, but generally speaking, the main difference is that we encode each utterance in the context separately, and we also encode the response separately. Okay, so often these encoders are actually similar, if not identical, right? So they can be trained together, right? And then the output of these utterances are then matched one-to-one with the response. So in this case, you can see that utterance 1 is paired up with the response, okay? And then into this, there's another matching unit, right? So this matching unit essentially computes sort of a similarity between this utterance 1 with the response, all right? And then for utterance I, we also compute its similarity with the response in here, okay? So we do that for every utterance in the context with the response, right? So this way, we sort of get the pairwise similarity score or representation between the input and the output, all right? And then we aggregate all these matrices together, okay, into one big 3D matching cube, sort of a cube-like thing. And this is a representation that's why we call it hierarchical, because we do the pairwise first, and then we aggregate everything together into a final matching score, right? So in the end, we still get a matching score, just like the previous case, right? So this picture actually shows you what we call a deep attention matching network, right? So this is the second category of approaches. The third approach, which is also the most widely used approaches today, makes use of the pre-trained language model, all right, such as BERT. All right, so here we concatenate all the utterances in input into one big long string, and we use the response as an output string, all right, output sequences. Now, what's different is that instead of sending them into the bidirectional LSTM, we send them into a context encoder, which is typically this context encoder is a pre-trained language model, right? And then the output of this will be a distributional representation of both the input and the output, right? And then we basically select a subset of those, because usually this the thing is that all these models, they have certain constraints with the memory, right? So we will truncate the output sequence into the first m vectors, right? And then we send these m vectors into this attention module, right? And same thing, we send the candidate representation into this attention module as well. And finally, we still compute a score, all right? So in all these three cases, at the end of the day, we are training the whole model using this sort of a similarity score, okay? And this similarity score is the similarity between the input utterances and the output response, right? So now, having looked at these previous approaches, right, you can see that most of them have to concatenate the utterances into the input, right, into a sequence, one way or the other. But when you concatenate the utterances together into one long sequence, the downside of this is that the dependency information between the utterances which are not next to each other becomes lost, right? So we lose the dependency information between utterances, especially those utterances that are far apart from each other, all right? So, but if you observe these, whether it's two-party or multi-party dialogues, you can realize that very often the dialogue session actually is made up of multiple dialogue threads, okay? And these threads actually entangle with each other, and they mix together to make the entire session, all right? But each thread actually talks about, sometimes it talks about one topic, right? Sometimes they were sort of depending on each other, and they were responding to each other, right? So even though that you have two people talking to each other, it doesn't mean that the whole dialogue is just one thread, all right? A lot of times you can observe that there are more than one thread going on. Okay, so I'll give you some examples, right? So here, the first example is a multi-party example. So in this case, we have three persons talking to each other, all right? And this happens to be taken from the same data set as the previous example. So they are still talking about Linux operating system. So in this case, the utterances that are marked in green, they are actually responding to each other. And the utterances marked in blue indicates another thread. So this particular dialogue history consists of two threads, all right? For example, here, this B here says, stop all the services you don't need from loading on startup. So this utterance is actually responding to A, who said, how can I speed up Ubuntu's initialization process? Okay, so immediately after that, actually there's an interleaving thread going on in which C says that my grub menu wasn't displayed while starting Ubuntu help, right? So later on, B respond to that request. And he said, comment out the vars in the etc default grub and so on, right? So you can see that clearly in this history, there are two threads going on here, right? Now, if I ask you what is the right response after you've seen all these utterances, okay, the ground truth, this is the ground truth. The ground truth is actually B, okay? Those are all services that load on startup, which actually follows A here, because A said, I have no idea what these files are for, but B has an idea, so B actually tells them that, okay, these files are for the services that are loading on startup. Okay, the next example shows you a two-party dialogue history, okay? So this is actually a dialogue between a patient and a doctor on a health consultation forum, right? So this is a dialogue, but it's actually not a real-time dialogue. There's a bit of delay because these two guys are typing to one another. So there are actually times when one person actually says two things, but the other person only were responding to the second utterance first. Okay, here's an example. The patient says, I'm 18 and I have fever for 2 days. What should I do? All right, and the doctor responds to that by saying, do you have any symptoms? And at the same time, after that, immediately after that, the doctor asks, have you taken any medicines? All right, so it turns out that this patient probably saw the second utterance from the doctor first. So he responded to that and he said no, okay? And you know that that no is not a response to the symptoms question, because after that, immediately after that, in U5, the patient said, I feel sore all over when I got up and I got stuffy nose and a bit of headache. So these three consecutive utterances were actually the responses to the first question by the doctor. So you can see that the order of these utterances are not completely lined up, okay? So if you chase the dependency among these utterances, you realize that the green ones are actually in one thread, whereas the orange ones are in one thread, the blue ones is another thread, okay? Simply because the blue ones, the first utterance from the blue one was actually an initial question, which is, what should I do? And the second utterance from the blue thread says that, okay, you're supposed to take some medicine for high fever, right? And then you go to hospital for a blood test, right? So this is another example that shows you that even in two-party dialogues, there can be multiple threads going on, and the utterances within one of the threads depend on each other in a more sequential fashion. All right. So this is the observation that we have, right? So now, given this observation, essentially what we are thinking about is that instead of modeling the context as a sequence, we model the context as multiple threads instead. All right. So, but the question is, how do we extract out these threads from the dialogue context, right? So we take advantage of the discourse parsing technique, which was actually one of the standard tasks in natural language processing. But historically, discourse parsing were used on normal text and not on dialogues. But more recently, people have developed certain systems and theories for discourse parsing on dialogues as well. So we were actually able to take advantage of some of the ideas in there. But the difference here is that we are not actually labeling the discourse relations in this work. Instead, we are only interested in knowing whether an utterance is dependent on another utterance. So what we're doing is sort of like a dependency parsing, but at the level of sentences or utterances. All right. So here, for example, let's say this is our initial conversation, right? And the arrows, the blue arrows here indicates a dependency. For example, T4 depends on T1, okay? And then T7 depends on T4, okay? And the numbers here indicates the strength of that dependence, all right? So we actually train a stripped down version of the discourse parser, which we call utterance dependency parser in this work, all right? And this dependency parser can actually give us the score for dependency. And for those dependency that has very small score, such as this one, we will just ignore this edge, all right? So at the end of this dependency parsing, we'll be able to come up with a parse tree, okay? And using this parse tree, we can get out a number of threads from this original context, right? In the case of this conversation, we managed to get at least 3 threads, right? Like the first thread is T1, T4, T7, and the second thread is T2, T3, T6, and so on. All right, so after that, what we do is that we still take the original, the input, okay? So the input, we actually segregate the input sequence into a number of threads. So in this case, C1 is the first thread, C2 is the second thread, and CM is the mth thread. Okay, and this R stands for the response. So the general architecture actually looks very similar to the last one, the language model inspired kind of approach that I showed you earlier. Now, this C1 actually is a sequence of words. It's a sequence of it's a sequence of threads for each thread, right? So this thread, this C1 stands for a thread, which stands for a number of utterances. Okay, and here we actually just line up all the words within the utterances together. We chain them together in a long sequence. All right. So each thread encoder will take the sequence and it will output the vector representation, and then it goes into this aggregator, and then finally going to this this attention mechanism. So the rest is actually pretty similar to what you saw earlier. All right. Now let's take a look at the evaluation result. Right. So here's an example. All right. Given this particular conversation, our dependency parser is able to take out 2 threads from here, right? For example, here, the first person says, how long does a package wait in the proposed queue till it makes proposed, okay, till it makes? And the answer is supposed to be this one, okay? Some like to say a new FF update, blah, 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 but it's ported to an early version. So this is the response to the first one. And then the next one said, I'm confused by this comment. So this comment was actually referring to this particular comment, all right? And then the blue thread actually indicates that, okay, this one has no real time span, so this guy is responding to this. And then the first guy actually says thank you to the second guy. So you can see that there are actually more than 2 guys in this particular conversation. All right, now given this example, right, in the previous approaches, what we actually do is that we concatenate everything together into one long sequence. So that's like our one long thread in this case, right? But the output, okay, the actual correct output, which is the correct response here, it should be, looks like it says fixed. The development release will be released on the October 28th, and this was the actual ground truth output, right? So if you compare this output with the input here, you realize that some of the stuff here is actually noise. For example, this one, no real time time span is down by individual team at times, so you have to watch it for it basically, right? So this particular one was actually noise, and given this noise, it would actually do more harm than good, and you could actually, the model can actually return something different than this one, all right, because of this noise. So in our case, we actually split up the original input into two threads. Okay, one is this thread, the other one is this thread. So we end up with two sequences, all right? And according to the model, the first sequence actually contains that piece of noise, right, which is no real-time span, blah, 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 right? And the second thread is actually the one that you want. So the model actually is able to compute that the ground truth is actually more similar to the second thread than the first thread. So given the fact that we have two threads, we are now able to eliminate or at least reduce the possibility of producing incorrect results. Okay, so we have more opportunities to get closer to the actual result. Okay, so statistically, if we compare our result, which is indicated by thread bi and thread poly here, okay, the difference between thread bi and thread poly is that in one case we're using the bi-directional encoder, bi-encoder, which actually takes the input from pairs, okay, pairwise encoder, and the other one is using poly encoder, which means we actually use a hierarchical setup, as I showed you in the very beginning. All right. So it turns out that in the three data sets that we experimented on, which are Ubuntu v2, which is the data set that you saw earlier, where most of our examples were taken from. Okay, and then we have the DSTC7 and DSCT8 data sets. So in all these examples, right, we can see that our thread bi and thread poly behaves consistently better than all the other baselines. Okay, perhaps except for the cross encoder in this particular case. Okay, but the cross encoder is extremely expensive. This encoder actually needs you to compute the score between each and every utterance, all right, in the input and with the output. So this one has a better score for Ubuntu v2, but it's very, very expensive. In fact, if you do this with this DSCT8 data set, it ran out of memory. All right, so we couldn't get a result. Okay, so that was our first work on dialogue response selection. So next, I'm going to talk about another sort of an interesting acute problem that we did recently, which is called clarification question generation. All right, so this is this work was actually inspired by some observation online. Okay, so this example here is taken from the Stack Exchange forum where people discuss technical problems. All right, so we see that in the beginning there's some guy who's trying to install a package. Okay, and then he was asking that he's looking for a certain library, but the installation program doesn't find it. So he's trying to seek help here. Now, after a reader saw this message, this guy actually asked a question. Okay, he asked, what version of Ubuntu did you have? All right, so this is actually a clarification question to some extent. Okay, and the reason why the user asked this question is because he's not able to provide an answer unless he knows this bit of information, which was missing in the original post. Okay, now having seen this comment, okay, from the other user, the original person who asked the question actually amended his or her message, all right, by saying that, okay, I'm aiming to install APE in Ubuntu 14, blah, blah, blah. Okay, so he or she actually made a change to this actual message to make it more obvious, to make it more clear. All right, so the moral of the story here is that sometimes you can get a situation where you're trying to say something to a crowd, okay? But what you said is too vague or too ambiguous, all right? And at this point in time, if certain clarification question can be generated automatically, it can remind you of that certain information is missing, all right? And then you can possibly make changes to your post or to your message to make it more complete, all right? So to give you another example, all right? So this is a post given on Amazon where somebody was trying to sell this waffle maker, okay? So when this original post was posted out, it actually attracted a number of questions from the readers. For example, this reader asked, does this contain Teflon? All right. And another guy asked, will the mini waffle fit in a toaster to reheat it, or is it too small? Okay. So, and another guy asked, how long to cook a waffle? Okay. Not even a hint in the instruction. So given that since we see these things, right, we realize that the customers actually care about some missing information in the original product description. So the customers actually ask questions, but it could be a situation that because of this missing information in the original description, it actually deterred the users from buying this particular product, right? Which is really a bad thing, right? So all these observations led us to propose this sort of a new problem, which is we want to actually develop a writing assistant, okay, in which it allows people to write, for example, a product description, such as in this case, you're writing a description for a waffle maker, right? So you're putting a title for your sort of advertisement, and then you're putting your description, right? So at this point in time, we want the systems to generate questions. So after you finish your message, right, you click on the question button, and the question button actually the system will go through your message, and it will determine that what is missing, what important information is missing from this message. For example, here, the system may automatically generate questions such as, what is the voltage of this machine? Okay, what are the dimensions of the waffle maker? What is the wattage for this machine? All right, these are informations which are missing from the original message and which might be interesting to the users. Okay, so we want to be able to generate this kind of stuff, and then the user, the original content creator, can suitably add the bit of information into the original message, all right, so as to make it more complete. Okay, so this is where we come from. Okay, this is why we're doing this job. All right, now if you come to think about it, right, the main challenge of this problem, which is automatic clarification question generation, is that it's actually asking for information that is missing from the context. All right, so this is actually quite different from many of the existing text generation problems. Okay, typical text generation problems basically ask you to make some alignments. So the output message is often in some other form exists in input. For example, you take machine translation, right? The output sentence is just the same meaning of the input sentence, except in a different language, right? If you take summarization as an example, the input is there and the output is actually a subset of information from the input, right? So in most of these existing text generation tasks, we are interested in generating things that are somehow already in the context, in the input context, okay? But this is not a case in the CQ generation task. Here, we're looking for information missing from the context, okay? So this is the challenge number one. Okay, the challenge number two is that the question that we generate should be specific to be useful. Okay, now to show you what I mean by specific, right? Now, if you are selling a product which is a electronic device, right? Electronic appliances, it makes sense for you to ask for what is the voltage of the thing, right? Because I may want to carry this to another country, right? And it makes sense for you to ask questions such as what is the wattage, right? Because I want to know the power of this, the energy consumption. But it's less useful if you're asking the questions such as what are the dimensions of the product? Well, it's not that such question is not useful, but it's a very generic question which can apply to any product, right? So we would like to generate questions that are more specific to the product that you're writing the message for, okay? So that's the second challenge. The third challenge is that we want to be able to generate a diverse set of questions, okay? Not just one question, but we want a whole range of questions that covers a wide range of user needs, okay? To give you an example, right? In the first case, like if you are asking questions for a electronic device, right? It makes sense for us to generate a set of questions such as what is the voltage? Does it contain Teflon? How long does it take to cook waffle? Okay, because these questions, they cover different topics and sort of a variety of topics that might be interesting to the users. Conversely, if you take a look at the second example, right? Here, the three questions that we generate are, what are the dimensions? What is the size? What is the height? So obviously, these three questions are highly related, okay? So we call these questions repetitive, and they are not so useful. All right. So in conclusion, the challenges of these problems are we're looking for missing information in the context. We want the question to be specific. And then finally, we want the questions to be diverse. Okay. Next, let me talk about the approaches that we're going to adopt here. Okay. Our basic idea is that even though that the questions that we generate may not exist directly in the context itself, there can be certain hints that we can take from the context. Okay, in this particular case, we're talking about keywords. Okay, keywords that are content words, which means they're not stopping words. And in this particular work, we take verb, noun, and adjective words as possible candidates for keywords. Okay, now what our idea is that the main content of the question can be covered by some of these keywords, right? For example, if you're asking what are the voltage, right? Voltage is the keyword, right? If you're asking, can you chop nuts and blend items together? Okay, this one I suppose is a blender, right? We're trying to sell a blender. So chopping the nuts and blending items, these are the keywords, all right? Now, the idea here is that we want to be able to first generate the keywords, okay, and then control the generation of the whole question by conditioning on the keywords. All right. Now, if you want to generate specific questions, then you give very specific keywords, right? If you want to generate diverse questions, then you provide a group of different keywords. Okay, or different groups of keywords. Okay, like for example, if I want to ask questions about the dimensions, then my one set of keywords will contain things like sizes, height, weight, that kind of thing, right? But if you want to ask the wattage, right, another set of things, set of keywords will include words such as energy, power, wattage, and so on and so forth. All right, so we can actually use keywords to achieve the two goals that I set earlier, which is specific and diverse. So this is the basic architecture of this approach. So the key idea is in this red box part, okay, which is keyword predictor and keyword bridge, and then we have a keyword selection here. All right, so let me talk about these few modules in turn. So in the keyword predictor, our input is the context, which is the message, right? And our goal is for each word, our goal is that for each word in the pre-extracted keyword set, decide if the keyword if it is a keyword of the question. Okay, and this amounts to a multi-label binary classification problem. And in this case, we use a text CNN model to do that. So we didn't invent that, but we just take it as a tool, right? The output of this text CNN model will be a keyword logis, which is the probability of a certain word being the keyword in the final question. All right. So, and then once we have that, right, we basically have this is a list of all possible keywords. So essentially, these are the words that we like I said earlier, these are either noun or verb or adjectives. Okay, nothing else, just a set of all these possible words. And now after the previous step, we are able to basically assign probability to each of these words, right? And then we rank them, and we take the top K, or we set a threshold, right? So that will give us a set of selected keywords, right? After that, what we do is that we do a clustering of these keywords, right, into different groups. And the reason why we do this clustering is, like I said, we can be more we can be more diverse, right, once we have the clusters. So the selection part actually is going to give us things that are more specific, right? And the grouping part or the clustering part give us questions that are more diverse. Okay, so essentially the clustering will ensure that the clustering will ensure the coherence with semantic information within the group. All right, so in this case we use spectral clustering on word co-occurrence graph. Okay, so we actually cluster on the graph, the word co-occurrence graph, and it produces different groups to condition on for diversity generation. Okay, now once we have these different groups of keywords, right, the next thing we do is actually do the generation of the questions. So instead of the conditional, the traditional generation method essentially rely on this kind of language model, right? If you're talking about sequence generation, right, usually we say, okay, we want to generate Y given X, where X are the previous words that have already been generated, and Y is the next word to be generated, right? So here, different from this approach, we use something called keyword condition generation. So instead of just conditioning on X, which is the context, right, which is the previous words generated, we also condition on ZS. So ZS is the set of, is the selected set of keywords. All right. So this is done using the keyword bridge, right? So this model, essentially, this model is done using the keyword bridge module. All right. And for example, right, if our X is Belgian waffle maker, right? So this is the set of things in the context, all right? And our keywords are voltage and machine, right? So given this context and this set of keywords, what is the question that we should generate? It's what is the voltage of the machine, all right? And another example, let's say your context is dimension waffle maker, right? And then these are the keywords. The keywords are dimension waffle maker, and the context is still Belgian waffle maker, right? And then the generated question should be, what are the dimensions of the waffle maker? All right. So these are essentially this. By the way, this X, right? This X is also keywords taken from the original context, not the whole context, but the noun, verb, and adjectives that exist in that context. Okay, now let me show you some results, right? So our key comparisons are the MLE, right, and the HMUP, these two baselines, right? So the MLE is a vanilla seek-to-seek model trained with the maximum likelihood estimation objective. So the diversity, right, is achieved through using beam search, right? So because if you look at the final output from this seek-to-seek model, right? If you look at the search beam, you can actually find a number of different possible outcomes, right? So if you want to achieve diversity, our approach is that we can just take the different questions from the beam, all right? Now, the second baseline is a one representative approach of mixture of expert model for diverse machine translation. Okay, and we adapt that onto the CQ generation problem. And we achieve diversity from the model's mixture distribution. All right. And finally, our approach is called KPC net cluster. Okay. And this is the best KPC net variant, which means we include the clustering, the spectral clustering on this model. Okay. There are other variants which doesn't have the clustering, which I will show you as a comparison in the later experiments, the ablation test. Okay, so let's first take a look at the result, right, of the KPC clustering result. Now, let's say your product, okay, your product is a novel foam, memory foam comfort curve pillow. Okay, so this is the pillow that you are trying to write about. All right, so let's say these are the keywords that we get out from the message, right, and we're trying to generate some questions from there. All right, now it turns out that we can generate at least these two questions. The first question is this a firm pillow, right? And we generated this question given these keywords, okay, which are pillow, foam, sleep, and firm, all right? So these are the keywords, all right, that we condition on. And the second question is this pillow good for stomach sleepers? And we generate this question from the stomach and sleeper, these two keywords. All right, so you can see that these two questions, they are not similar to each other. All right, and they are all both pretty good. All right, so but okay, this is another example. Let's say our product is Home Legion's 2588's accent dining chair, blue-gray set of 2. Right, so these are the results generated by 3 different methods. All right, so you can see that the first one, MLE says what's the seat height, what are the dimensions of the chair, what are the dimensions, right? So you can see that all 3 questions are actually very much related to each other. Okay, perhaps the first question is more useful. Okay, but all 3 are actually equivalent. And they're not so specific because anything can have a height, right? So that's our conclusion here. And then for the second baseline, right, it generated these 3 questions. Okay, what is the weight limit for the chair? This is good. This is a useful question. And then the second one is I have a table that is an UNC. So this UNC means that it's actually trying to generate a word that is not in the vocabulary. Right, so it produces an unknown token there. Okay, will this chair be able to fit on that table? All right, so this is a very strange thing because you're asking for something that is pertaining to a product that's only owned by this particular user, right? So this is not a very good question, right? Okay, the third one says, is this a set of 2 tables or just 1? All right, we deem this one to be a repetitive question because we actually already said that in the title, right? In the context, we said this is a set of 2, is a chair, which is a set of 2, right? So asking for set of 2 is not useful, right? Because we already know that information. Now, if you look at the 3 questions generated by our approach, right? The first one is what is the color of the chair? This is not useful because we already told you it's blue-gray, right? The next one is what's the dimension of the seat? And the last one is what's the weight limit? So both of these 2 questions are useful and they're diverse and they cover specific aspects. So overall, we can conclude from this example at least, right? KPC net does a better job than the two other approaches. Okay, so in general, to summarize, the MLE approach tends to generate universal questions for higher likelihood. So they will ask questions which are very general, okay, catch-all kind of question. And they're likely to overlap with each other because we were using beam search. In the second approach, it generates diverse questions from its mixture distribution, right? But the latent variable for the mixture is not explicitly supervised, so it's hard to interpret and control and produce, and sometimes it produces strange outcomes. And for us, we generate specific questions because of the keywords, and the diversity comes from conditioning on the keyword set, right? So overall, we are doing a better job. Now, related to this CQ generation, right? There are other people who did some other work which also generate clarification questions. In this case, in this particular case, they were generating clarification questions for information retrieval, right? For example, somebody was searching for a keyword headaches in Bing search engine, right? So Microsoft can actually ask the question, what do you want to know about this medical condition? So this is actually a clarification question for information retrieval. Once the user answered this question, the answer will be combined with the original search query to get back more targeted search results. Okay, there's some other work on clarification questions for dialogue systems. For example, this user says, I'm too fat. And the machine asks, how about climbing this weekend? Right? And then the second example says, the user says, last night I stayed in KTV with friends. And then the machine says, are you happy with your singing? Right? So this kind of clarification question is also useful in a sense that a machine can proactively engage the human and not always be passive and passively answering questions. Right? So this is sort of a new paradigm for the chat system or dialogue systems to be more active and proactive. Right? So this is related to our work, and in some sense, they are also generating things which are missing from the context. For example, the climbing, right? The climbing is something actually not existing in the previous context. And the singing here is actually related to the keyword KTV. But the singing wasn't actually in the original context. Okay, so in conclusion, we designed a writing system to help people who write these descriptions, right? And we can generate questions using the KPC net, which are specific and diverse. Okay, and there's actually more to be done. Okay, for example, we can leverage external knowledge in future to improve the keyword prediction. Okay, finally, let me talk about our recent work on abstractive summarization using what we call the Extractor Abstractor framework. Okay, so let me first say something about the abstractive summarization. So this is an important problem in natural language processing in which we are supposed to produce an abridged version of a piece of text that contains the key information which are relevant, okay, and important. So this particular task finds many applications. For example, in newsletters where we are supposed to produce the digest and the headlines, okay, of news pieces, and we are trying to squeeze everything into a small display, such as a mobile phone, right? So you have to summarize the content into just headlines, right? And also for producing digest, like digest from earning reports and financial news, which can be very cumbersome and tedious, right? So we produce just a short summary for the executive to read in their very tight schedule. Okay, now, given the fact that we want to produce an abstractive summary, which means that we actually want things that are not exactly the same as in the input, okay? So the abstractive summarization here is in contrast to extractive summarization, in which we just extract certain sentences from the input and then put them together to construct a summary, right? So by contrast, the abstractive summarization essentially generates the whole summary from scratch, all right? And the wording, the use of word is supposed to be different from the input original document. So the key idea here is that for summarization to work, we need better alignment between the source document and the summary, right? So our key idea here is that for abstractive summarization to work, from a human perspective, right? If you ask a human being to do this kind of task, what he or she will do is probably first take out the most salient content from the source document and then paraphrase the selected content to generate a summary, right? So this is what a human being will do to complete this task, right? So what we want to do here is to simulate this process. And we realize that keywords, again, just like the previous work, we realize that keywords can be useful here to select the salient content word. All right, so here's an example, right? Suppose our document here is taken from the financial news portion of the China Daily newspaper, right? So in this particular case, it's actually talking about the banks helping the small and medium-sized enterprises to overcome the coronavirus-related challenges, okay, and take the country's reform and opening up, etc., etc. Okay, so the key thing here are actually highlighted using the italicized fonts. So the summary, if I want to create a one-sentence summary for this, right? The summary should be China's banking and insurance regulators vows to support the small and medium enterprises, right? So this is the key message of this source document. And you can see that this summary actually doesn't exist exactly in this document. So it's actually sort of cooked up from this first sentence and this sentence here. So it's actually a combination of information from this sentence and this sentence, right? So that's the idea. So now our idea is that if we can take out the first two sentences, okay, and then we can take them out by recognizing certain keywords in those two sentences, right? In this case, the keywords are bolded, right? So for example, China's banking is a keyword, right? The help is a keyword. The SME is a keyword. And the insurance regulatory commission is keyword, right? So, but then how do I get these keywords? The keywords are actually taken from the reference summary that I showed you earlier, okay? Because you remember we were looking at the regulators and they were helping vows to help the small and medium enterprises, right? The banking industry and so on. So those were the keywords taken from the reference summary, and we realized that those keywords also exist in a source document. And in particular, they exist in these two sentences in the very beginning of the news. So the idea is that once we get these two salient sentences, right, we would then just paraphrase the selected content, right? We would then select out these keywords, okay? For example, the banking, the help, and then the commission and so on, right? And then we paraphrase these words to get the final summary, right? So this will be the basic flow of what's going on. Now, to translate that flow into an architecture, here's what we call the extractor-abstractor model. Given the initial documents, right, we take the extractor will then extract some salient sentences, right? And then these salient sentences are sent to abstractors. Notice here the abstractors are not just one, but many abstractors lined up in parallel. So the advantage of that is that we can now do the abstraction generation in parallel, right? So that saves time. Now, the output will be the final summary, which consists of a number of sentences. So each input sentence produces an output sentence. So the abstractor serves the purpose like a paraphrase, a sentence that will paraphrase. Now, what's critical in this architecture is that in order to train the extractor and the abstractor, we need ground truths here, okay? And this ground truths in this red box is what we call pseudo summary. So the pseudo summary are actually extractive summary. So they are extracted, these sentences are extracted from the documents, okay? And then these sentences will be used to train these abstractors, right? So the critical question that we want to ask is, how do we create these pseudo summaries for training both the extractor and the abstractor? So let me now show you the detailed approach, right? So suppose that these are our, this is the ground truth summary sentences, all right? So what we do is that we need to find the most similar sentences in the original document. They may not be exactly the same, but we can use keyword overlap to find out the most similar sentences in the source document. So what do we mean by keyword overlap? We mark out the keywords in the reference summary sentences, And we also mark out all the possible keywords in the source documents, right? So we would then compute the similarity between each document sentence and each summary sentence by computing the amount of overlaps with the keywords, right? For example, and also here, we're not doing a one-to-one computation, but rather we're computing the similarity between a set of document sentences and a summary sentence, okay? So for example, here, document sentence 1 and 2, they're found to be together similar to sentence 1. And then document sentence 2 and 3, they are found together to be similar with sentence 2, okay? So the reason why we want to combine these sentences into sets together is because sometimes we realize that you can have a long sentence that talks a little bit, which is more related to the first sentence, and then the second half of it, it may be talking about something else, which is more related to the third sentence, okay? And as a result, the summary sentence may actually be combining the information in not just one source sentence, but multiple source sentences, okay? So that's why we're taking this set approach. Now, because these, in this case, right, the 1, 2, and 2, 3, they are actually overlapped in the sense that the sentence 2 appears both in set 1 and set 2, right? So we will actually merge them together into one, and then we also merge these two reference sentences together into one. Okay, this is just some detailed approach that we adopted here in this paper. Okay, and then these documents they are going to be merged with this, okay, into this third sentence. Okay, now in order to do the extractor, right? So we use something called a keyword-based extractor. So I probably won't go into the details of this. Essentially, it's following this sentence encoder and document encoder, and then we also use a pointer generator, pointer encoder, to make sure that we know the right boundary with the beginning of the sentence set and the end of the sentence set. Okay, and for the abstractor, we use a very popular sequence-to-sequence model, which is modeled after the popular BART model. Okay, so it's actually pre-trained on BART. Okay, now the next critical thing that we do is that because we have two models, right? We have an extractor and we have an abstractor. So how do we train these two models together? Given the fact that we have these intermediate summary, okay, the DJT here is the intermediate summary, right? So how do we sort of combine them together and train them in a single model? So our solution to that is to use a reinforcement learning framework, okay? Essentially, our reward for the reinforcement learning comes from two sources. One is the loss, the final loss, which is the difference between the generated sentence and the summary sentence, okay, the ground truth, right? The other one is actually the gradient. The other one is this, is actually the loss in the extractor part, okay, the extractor part. So we actually take two different source of input to combine into this reward, and then we train using the gradient policy gradient update, and then we train both extractor and abstractor at the same time. Okay, so it makes this an end-to-end trainable model. Now this is for the agent, right? Essentially, it goes through these steps. It receives the state ST, and then receive the reward and execute an action, which is pretty standard in the reinforcement learning. Okay, then finally, let me show you some experimental results. So here's an example source document, right? In this case, they're talking about in New Delhi, police found out some secretly positioned cameras in the changing rooms of a clothes shop, right? So and they took certain people for responsible for that, and they are going to spend some years in jail, right? Now, if you look at our result, right? Our extractor first extract from this source into two sets, and these are the two sets of sentences. So here you can see clearly that these two sets of sentences contain the crucial information, such as, okay, when the education minister visit this Fabringer outlet, in the tourist result, right, she realized that there's a surveillance camera pointing at the changing room, okay? And then the authorities found overhead cameras, okay, which were actually taking pictures of the customers. And then the second set, the first set was talking about how they found out this incident, right? Found out the fact that the cameras were used and shooting customers. And then the second set of sentences says that the employees of the shop has been arrested, and if convicted, they will spend up to 3 years in jail, right? So this is the outcome of this. Now, if you look at our final result, right, given these two sets of sentences, our abstractive summary will be something like this, right? For the first set, we generate 2 sentences. For the second set, we generate another sentence. So these sentences are essentially the rewriting of the original, this intermediate results, okay? But you can see that it's a pretty good result because it actually talks about the minister visiting the store, saw the camera, and then realize that they can take pictures, and the photos are from the changing room, and the employees could spend up to 3 years in jail. Okay, now if you compare our result with some other result, for example, if you compare with the vanilla BART result, right, you can see that this BART result actually lose some salient information such as camera and the jail terms of 3 years. Okay, and it also contains redundant information such as here, summon 6 top officials from Fab India, which is not actually included in the ground truth summary. Okay, so our summary is actually better. Now, if you look at the numbers, right, our result is indicated by this highlighted box here. So our result, if you compare our result with all the other abstractive summary approaches, we are actually consistently better in terms of the Rouge 1, Rouge 2, and Rouge L results. Okay, although the gain here is not big, okay, it's less than 1 percentage point, but we need to realize that in this line of work, okay, any improvement like this is actually very hard to get because we're already hitting sort of the ceiling of the research. So it's actually very hard to improve the Rouge scores in summarization tasks. Okay, if we look at the speed and memory use here, right? So we are actually, in the case of testing, right? In the case of testing, our time use is much faster than BART, okay, and the pointer generation, and our memory is also much smaller than the previous 2 approaches, right? In the case of training time, we are comparable with the other approaches, and the BART actually goes out of memory. All right, so finally, let me sum up my talk. And today I actually talked about text generation, which is a very hard problem in natural language processing. So I gave you 3 instances which we worked on recently. And essentially our ultimate goal is to enable machines to talk, write, and interact just like human, okay? And some of the techniques that we developed here can be applied in certain limited scenarios at the moment and may not be completely generalizable yet. Okay, so that actually poses new challenges going forward. So and another big challenge in this line of work is the evaluation, because a lot of these text generation tasks actually can generate sound and plausible output without being similar or identical with the ground truth. So comparing exactly with the ground truth don't really make sense, right? So evaluation is a big challenge here. So there's still a lot of work to do, and with that I end my talk, and I welcome your questions. Thank you.
Thank you very much for the talk. We should have some questions from the audience, right? So any question? Yeah, Michael, you can just talk.
Yeah. No, I was working out how to unmute. It's always a challenge. Yeah, so this work is very interesting. I think there are huge opportunities for perhaps your students to collaborate with some of mine. So I'm very excited by this because we've been working on sort of similar problems in a sense. And that's why I have this general question. when you think about what's motivating the kind of broad sweep of your work, right? What do you hope to achieve at the end? Do you hope to achieve a commercial copywriter for product postings on Alibaba or Taobao? Right? Is that the end goal, or is there something bigger?
Right. Good question. Actually, when we came about doing this job, right, this clarification question, we were actually inspired by some of the discussions we had with people from Taobao and Alibaba. So they were actually interested to improve the interaction with their users. They have a lot of small merchants who post their product description every day. So they were actually thinking about improving the interaction and basically help these guys stay longer on their platform. Okay, so at that time we came up with this idea because, like I said, through the observation that sometimes actually users can be pretty fed up with the incomplete message there. So they ask questions, okay, because certain things are missing. And then if you keep having this kind of incomplete descriptions up there, it might actually disappoint the users, disappoint the customers, and actually eventually affect your final commercial interest. So at the moment, I haven't talked with them about this result, even though that this project was actually inspired by my conversation with some of the colleagues there. But I think it is definitely possible, right? We can actually talk about certain collaboration commercially later on. Any other questions?
Any question from the attendees? There's a one.
I see some message there in the chat.
Yeah, there's one question. Have you considered reasoning in your text generation?
Okay, that's a good question. Yeah. That's a good question. Reasoning is a big part these days. Reasoning can take in different forms. All right. Whenever you talk about reasoning, you actually think about knowledge, right? So you need knowledge to be able to reason. So at the moment, there are a few approaches to do this. One is to incorporate structured knowledge, such as knowledge graph, during the generation of text. So there are already works on that, which basically encode knowledge graphs and then encode these texts at the same time, and then sort of develop mechanisms to combine these two kinds of representations together, and then basically continue with the other part of the model, right? So that's one approach. The other approach is to make use of pre-trained language models, because there is a whole school of thoughts out there that believes that the language models themselves already contain substantial amount of knowledge, right? And the language models themselves, the pre-trained language models themselves, is actually able to reason to some extent. Okay, so because most of the works that I introduced today make use of pre-trained language model in one way or the other, so we consider that we are actually making use of some reasoning, although that kind of reasoning is not explicit, I would say, but I think they are making use of some reasoning. And this kind of reasoning is especially important in the CQ generation task. Okay, because in the case of CQ generation, we're trying to generate questions which are not explicitly there in the context. All right, so we need to find sort of relationships between the keywords to be generated and the words that are already there in the context. Okay, so I think some form of reasoning is already taking place there. Okay, but I think more work can be done there, possibly to make it more explicit and make it more interpretable.
Yeah, thank you for your comment. Just have one more question. So you mentioned using the pre-trained language model. So especially for the current natural language processing era, so pre-trained language model seems like a very strong tool that we can use. So is there any like the space for other model like the recurrent neural network or some other traditional model be used?
Yeah, well, certainly. One downside of these pre-trained language model is the size, is the sheer size and the amount of computation that requires to train them. Okay, so because of the limitation in normal people like us, you know, our computational capability, we normally just make use of pre-trained language models, right? And then we fine tune on our particular tasks. But if you really want to make changes to these models themselves, you will still have to train them. And that is going to cost you tremendous amount of time and also energy and electricity, right? So I would think that going forward, a number of ideas in these small but cute models, which can take advantage of both the language model themselves, as well as structured knowledge taken from other sources, is going to make it big. Okay, in fact, people are already talking about combining the symbolic knowledge with language models in the past couple of years. Like I said, there are already models doing that. But I would like to see more to be done in smaller models, which can fit into normal commercial machines. And this is very important because, you know, a lot of these devices, especially embedded devices, cannot have such large computation power. They don't have such large memory or GPUs, right? And which is why a lot of these applications that today we take common sense, for example, dialogue systems, for example, speech recognition, right? They only work on the cloud. They don't work on embedded systems, okay? The reason is that the models are too big. So I would certainly think that going back to those previous attempts, like smaller, simpler models, is not a bad idea, because in future, these models can work in small embedded devices, which are everywhere in our lives.
I'll follow up on that just for a second. So yeah, that kind of implies perhaps that you think that the neural component of this neural symbolic system is less information dense than a possible semantic adjunct, right? So if you imagine a knowledge base off on the side being accessed by a neural system, right? What you're saying sort of suggests that you think that the symbolic section is more compressed than the neural system, which seems dubious. Or is it just that you're saying that that symbolic system, you can store it in an inverted index on a disk drive or something in a way which is way cheaper to do than you know, sticking all the knowledge in the weights of a neural network? So
okay, good question. I think I didn't hear it very clearly, but I think what I gather is that you're asking me whether how to position the symbolic knowledge along with the large language model, right? Is that what you're trying to say? Trying to ask?
Exactly. And why do you think the symbolic models might be more compact than the large language models? Right?
Okay, more compact, right? The reason is, number one, if you look at the reality today, right? If you look at any structured knowledge, which whether it's human curated or automatically constructed, they are not larger than the language model that we are seeing today, even the modest size language model, all right? Simply because these language models, they are constructed, they are learned by very large models with a lot of parameters, and they also learn from huge corpuses. Whereas the structured knowledge, if it's curated by human, or whether it's crowdsourced or by experts, the volume cannot match the automatically learned models. That's number one. And number two, that the source from which we get this kind of knowledge is also different, right? The knowledge that we get from, the structured knowledge that we get from human, they come from human experiences, okay? So, and actually we value them because they come from a different alternative source, an alternative channel than from, for example, text corpuses. So definitely there are things that come from human experience, which don't exist in text corpus. So not only the size matters, but also I think the content also matters. The content that we get from structural knowledge, from the symbolic knowledge, is valuable because they complement and perhaps even contain, much of the knowledge that are already in the language model. Okay, so I think both of them are indispensable, but I think definitely we should put some stress on put some emphasis on the human curated knowledge going forward.
Yeah, we have many questions, but we cannot handle all of them. Maybe one more. Yeah, Brian?
Some of them were asking whether they can have a copy of the slides. Sure, sure. I will send it to Kai-Chi.
Hi, I think. Can you hear me?
Brian.
Can you hear me?
Yeah.
Can you hear me? Okay, cool. Yeah. So I have a question because I also working on multi-turn dialogue agent. So, but I'm so your question clarification model, you trying to make your question to be as specific as possible. But however, in normal conversational sense, when you do having a dialogue, usually it's not always, it's probably not ideal to have the maximum level of specificity of the question generated. So sometimes, when human have questions, sometimes you have a poll first, say, oh, did you study a university? And the person say, oh, yes, I went to, I studied a university in Oakland. And then you ask a more specific question about that particular university. So sure. I do see some potential of developing toward this kind of adjustable or, probably adjustable question generation by combining your question to clarification result with the thread finding result. I mean, the thread clustering, the second one. So do you have any?
Okay, that's a very good question. Yes, I understand your concern here, which is in the context of dialogues, the amount of specificity that you use in your questions should not be a fixed level, should not be at a fixed level, but rather, like you said, it's very natural for us to ask general question first, then we go into the specifics, right? So I certainly agree with that. The thing that I want to say here is that for this piece of work, because we are generating questions in a one-shot kind of fashion, that is, I see your message, right? Then I generate some questions for you in one go, right? So there's actually no continuous interaction in between the user and the system, okay? Therefore, we are trying to generate a set of questions which are as specific, as useful as possible. But certainly, I agree with you, for like anything, right? You can't go to the extreme, right? But the reason why we want to stress specificity here is because in most text generation models, the models tends to generate more general stuff. It's much easier to generate general stuff than specific stuff, okay? That is why we are emphasizing that our system is capable of doing this. Nevertheless, if we are doing a multi-turn question generation, all right, like in a dialogue case, like if I'm simulating a doctor talking to a patient, then certainly I agree with you that the question that we generated should be controlled. The specificity should be controlled in a certain way, all right? But in the work that I mentioned, we were already using the keywords to control the specificity, right? But the level of control, I admit that is not good enough. And I think certainly I'm looking forward to more work into that line. And if you're interested, we can certainly talk and perhaps we can collaborate.
Sure, sure.
Yeah. So thank you very much for the inspiring talk. I guess, I guess many of us should have some common research interests, like Michael and Mengfen and myself also work on some like similar research problems. Yeah. Sure. So we can keep in touch and move on for any collaborations.
Sure. I'm looking forward to talking to you guys again, and welcome to Shanghai. by any chance drop by to our campus and let's have a meeting face to face.
Yeah, for sure. Okay.
Thanks. Thank you, guys.
Thank you.
We'd love to
Thank
see
you.
you.
See you.
Sure. See you. Bye.